So, we have looked into how we actually find out the repair cycle for roof covering. That is what we have seen in the last class. We have seen in the last class. So, what we do is we first define what you call anticipated state, define them and remedial measures required and cost. Then for every 5 yearly from past data, we try to find out how much percentage of the area will be in a given state, and from that we estimate the cost. And when the cost of patch repair or repair is equal or more than the renewal cost, that is replace the whole thing, all of them, then we do renewal. So, that is what we have seen in the previous class, right. And then we have seen also related to painting. For example, also related to painting, external painting or similar sort of thing, what we said was that you can have options that washing every year. A second option could be you do wash one time, one coat and then paint, or maybe put a better paint every 3 years, and the cost is known. Then if the cost per unit area is known, you try to find out cost per year, but in all cases you can bring time value of money into consideration, that is interest rate and number of years involved. So, annual equivalent you can find out. I think that is all we have seen in the I mean basically you see it is like this. If it is let us say the anticipated state is small isolated blisters, for that we do patch repair. Now, even you see if a large area is there, as I said there are a number of buildings, one building may have a deterioration which is worse than small blisters, maybe large blisters, but then it is only one building, area is still small. So, we do again locally repair. So, this the cost would be similar as the patch repair, because the cost difference comes because of the setup cost. If you have to set up for the whole area, let us say you have 5 buildings or area is very large, maybe 50 into 50 square meters, right. So, 2500 meter square of a multi-story top roof covering area. Now, if the if it is extensive, if you find that 50% of the area is in bad shape, right, and then 50% multiplied by 300 rupees or 3 times compared to if you do the whole 2500 like 1250 multiplied by 3, or 60%, 60 into 60 will be 60% would be actually say 60% of 2500 will be how much 1500 multiplied by let us say 300 or 3 units compared to 2500 into 2. Now, this would be how much? This would be this the 200 or whatever it is. So, you forget about this 200 terms, this is 5000 and this will be 4500. Now, you can see that they are nearly comparable. So, when the cost is let us say this goes to 1600 or something like that or 1700, then obviously, it is better to do the total area repair. Although, in this one the cost there will be some areas which is really in bad condition even in state 4, but then if the area is only 10% is in state 4, I will still do patch repair as and when it comes. So, the cost of patch repair or simple repair is essentially because for doing that 10% it is over 5 years of time. So, sometime in 3rd year or 4th year I may have to do, but then they will come set it up and then do the repair and go away. But then after let us say 25th year I decide whatever comes bad, already 70% is in bad shape, which will require large scale repair, I do the everything. So, another 30% which was still good I will do the repair. So, that everything is renewed now and I start afresh, that is the idea, that is the idea. So, that is why doing bulk repair is quite often advantageous, and that is what I think I was telling you in the last class, that is what I was telling you in the last class, right. So, and then you can bring in time value of money wherever required. For example, as I said, you can find out annual equivalent of money, that means every year how much you should be spending. Supposing 2 things have got different lives, say one alternatives have got a life of 7 years, another has got life of 5 years. while 5 years you spent less, but 7 years you spent slightly higher. Now, you want to find out, compare all economic alternative which is better. Find out what is called annual equivalent of money. That means, if you have spent 7,000 now, equivalent to how much money every year for next 7 years. Another one, if I spend some money now, how much is equivalent money every 1 year for next 5 years. Now, all that assumption I am making, that after 7 years again I will do the same thing, after 5 years I will do the alternative second again. So, this is the assumption I make, and that is how we do engineering economics computation, I mean rather comparison. That is what I was mentioning in the last class. So, similar situation can arise in many cases. For example, X is the repair and life is n1 years, repair cost, and Y is the replacement cost, and life, its life is n 2 years. Then interest rate is I. So, if I spend P now, after 1 year it will be P into 1 plus I, and annual equivalent is given by this formula, x into 1 plus I to the power n divided by 1 plus I to the power n1, because n1 year is the life, into I divided by 1 plus I minus 1, or it is like this, x into 1 plus I to the power n1 years is the life, right, into I divided by simply I, because and if I want to find out is, I mean basically if x is what I am spending now, because the series that I talked about. So, y similar one for y you can find out, and whichever gives you lower value, this factors would be same, only year, number of year would change here. It will become n2 1 plus I to the power n2 into not I mean into, I think there is a mistake somewhere there, minus I think. We derived this in the last class. So, whatever the annual equivalent formula we will have to use, I mean we can again derive this. In fact, you can just do this, because we said this is a GP series 1 plus I to the power n minus 1 divided by I, right. So, that will be the future sum, and if I divide by 1 plus I to the power n, then I get the So, this would be 1 plus I to the power n minus 1, this is what it would be, and 1 plus is simply 1 plus I to the, right, that is right. So, anyway this formula is, so if I have A every year, its future sum, present what value is, present value is this much, A multiplied by all this, and if I know the P or X I am spending now, I am spending X now, then it would be equivalent every year, yearly equivalent to 1 plus I to the power n multiplied by I divided by 1 plus I to the power n1 minus 1, and for the second case y 1 plus I to the power, I mean this term is within bracket 1 n2 minus 1 into 1 divided into I divided by 1 plus I to the power n2 minus 1. So, this is n1, this gets replaced by whichever is lower, you will take decision in favor of that. So, you can bring in time value of money. Now, this can happen sometime. For example, when let us say I have now I am repairing, one option is to keep the same system, say roof covering system, same system, right, whatever was there, and it will have a given life which I know. But many modern materials might have come, modern system might have come, better waterproofing system might have come. So, if I put it now, it might live for longer period of time, but the cost might be higher. So, I would like to compare which one shall I do. Shall I keep the old one which will have, let us say n1 years of life, or if I put a better one which will have slightly higher life, n2 years of life. So, which one do I select? So, this kind of decision making can be done, repair replacement decision we can use these concepts we can use, annual equivalent of maintenance cost we can utilize, right. So, that is what it is, right. So, time value of money can be utilized in this manner, time value of money can be utilized in this manner, right, as required in repair and replacement decisions, right, repair and replacement decisions. Okay. So, that is it. Now, Okay. Now, having done that kind of thing, I should be able to find out the renewal cycles for many items or systems, you can say. And we have seen that we can actually all the items in the building, I can classify them into several classes. Some of them will slowly deteriorate, some of them will deteriorate and then I'll replace them or repair them. Some will suddenly fail, we have classified them. So, now I can take all the items in the building and classify them. For example, I said that normally frames, structural system, foundations, etc., should not be requiring any repair. So, if I identify them, if I am able to identify them, in that case I can find out, I can do a planning right in the beginning of my, right at the time of construction, that what would be my projected maintenance cost from time to time for a given building or a set of buildings which are constructed at a given time or set of similar buildings. Let us see how do we do it. So, one way is to do is to let us say this, I will come back to first, I will have these slides, then I will go. So, for example, foundation. If you look at foundation, initial cost is 7%, let us say 7% of the total cost of the building, right, and it does not require any maintenance. These columns are percentage of initial cost, this column 5 years, 10 years, maintenance cost during life 5, 10, 15. So, 0 to 5 years all the cost here, 5 to 10 years, 10 to 15 years and up to intended design life of 60 years we are considering. Frame, say let us say some percentage I have put in 8% and it does not require anything, that is what I am saying. Roof covering 2% is the cost and I have found out the renewal period is 20 years. So, my maintenance cost, major maintenance cost will come 20 years later when I will replace all of them. So, after that again 40 years I will repeat it. So, I will incur 2% cost here and 2% cost after 40 years, right, and this I know right in the beginning. Similarly, if you look at it, external decorations 0.5% of the building and every 5 years I have to do that, 0.5% I will incur. So, I can put it half, internal 1.5%, 1.5%, etc., etc., and external doors 1%, then 0.5% I know, 50% I will require to replace in 25 years or 30 years of time and so on. So, total I will have 100% cost involved, because initial cost 7%, 8%, 2%, etc., etc., all will add up to 100%. Some will not require repair at all, some will require periodic repair or renewal costs, and this I can actually find out. Then I can sum them up after every 5 years. So, after 5 years let us say x, after 10 years let us say y, and so on and so forth. Therefore, right in the beginning I can actually find out what would be the maintenance cost of the percentage of the initial cost, because why it is preferable to take it as percentage, after all there will be inflationary trend, cost index might change, but initial cost I know and how much will be escalated cost over 5 years, I can estimate, or when I am doing budgeting right in the beginning I express everything in terms of percentage cost. So, if I do this for the whole building, I can do this for the whole building and I will get, I can put it dot lines or whatever it is for all items for a given building or for each building itself. And once I have done that, then I will get this sort of thing. This I can plot, or I can use it in budgeting. So, what I know is that 0 to 5 years I need this much of money for maintenance, 5 to 10 years I will need this much of money for maintenance, and for whole 60 years, and you will find that at this point of time possibly there will be lot more, at this point in time there will be lot more, because there is a cycle of around 20 years and it will tend to increase at that point of time. So, that is how it is. So, one can plot this cost profile, this is called maintenance cost profile, as a function of time. So, this is time, this is the initial percentage of initial cost, 100% is here, and this is the maintenance cost. So, you can find that by 60 years of its life, nearly 90% of the things I would have replaced at least once or maybe more, sometime twice, thrice. So, I spent almost same cost or nearly same cost during the life period of the building for maintenance itself, but then it is distributed over 60 years of life. If you take time value of money into account, that means put interest rate, then this value comes down, because present worth of this value will come down. Whatever you have spent here, let us say this is something like 90% of the initial cost. So, 0.9 IC divided by 1 plus I to the power n will come, 1 plus I to the power. So, since this interest rate, if you take, this value will come down, because this will be sum total of, I mean whatever it is, because there will be some n value would of course vary, because it will be over many periods of time, right, first 5 years. So, if you take time value of money into account, it tends to show you that possibly it would always tend to ask you to delay the maintenance, because current value will be relatively less. So, if you take interest rate, this is what it would be, but you can find out, you can compare different buildings, different building system. So, this is called maintenance cost profile, and you can generate it right in the beginning itself, during the construction phase itself, that how much percentage of the initial cost you will be spending every 5 yearly for maintenance purpose. So, that is what it is, that is what it is, maintenance cost profile. Now, for higher interest rate, obviously repair decision is favorable, late repair and replacement decision is favorable. So, when you do that and you plot a histogram form, something like this, percentage of initial cost 0 to 5 years, you will find that the cost is less, this is cumulative and this is histogram plot. So, you will find the peak comes somewhere around 30 to 40 years, because many things would require replacement at that point of time. No? So, as time goes, and then once you have replaced them, again the maintenance cost will come down. So, there is a peak. Now, if it is a single say 50 meter by 50 meter square building, then this would be the profile. But if you have large number of such buildings, then what will happen? Then basically all the buildings would not be constructed at the same time. Like if you see this campus, as I said, 1960s it started, and you will find that 60s there are the main buildings came, academic buildings and some quarters, staff quarters came. Then the blocks were added time to time, block 3, 4, 5 etc. they were added time to time, right. So, they were added time to time, but they are similar kind of buildings again. If you see quarters, they are also started time to time, actually they have been added, similar kind of buildings, hostels they have been added time to time. So, when you superimpose such maintenance profile, you might find that actually they tend to even out sort of. For many buildings constructed at different times, the peaks would actually, just let me go to the previous diagram. So, another set of building might have started somewhere here, right, started somewhere here, and its peak would be somewhere there. Another set of building might have started somewhere there, and so if you have several such set of buildings started at different times in an estate, you will find that they tend to even out somewhere, because the peaks will be occurring at different times, and if you sum them up, superimpose one over another, you find that there is a tendency to actually kind of neutralize and balance. So, your total maintenance cost of the estate you can estimate from this, right, estimate from this and update it also, because you will add new buildings, it will get updated. But then percentage cost you can find out, if scientifically you can find out percentage cost you can find out, right. There is another aspect, of course, the other aspect that is there is another aspect is also there. So, this is one aspect. When you have large number of buildings of the similar kind or not even of the similar kind, there is a tendency in an area, estate area, or let us say some kind of a housing society, where of course buildings more or less starts together, but there are one or two, more than one housing society nearby by the same organization. You find that the overall maintenance cost tend to sort of uniform, becomes uniform over a period of time. So, this is one reason why it becomes. A second reason why it becomes is, you see, although we have said, let us say roof covering, we said the renewal period is 20 years. Right. So, all the buildings, supposing I was giving example of 7 hostels of the similar kind, constructed almost similar time. Now, each one might have an area of, let us say, something like 100 meters square of the rooftop, right. So, if 700 meters square or something of that kind, or something of that order, let us say. Now, it may so happen that renewal cycles I have estimated on the basis of my past experience. Now, there is certain amount of uncertainty in this, probabilistic, because it depends upon the environment, the rainfall and things like that, actual variation in the materials of construction and the system. So, there is a kind of uncertainty involved, that is, it is probabilistic. So, on an average possibly 20 years of time, most of the buildings would require renewal, but out of 700 meters square, maybe one building requires, out of 7 buildings or 8 buildings, maybe one building by inspection you have seen that it requires complete renewal after 15 years. So, actually it would be distributed in this manner, possibly something like, so let us say 1 out of 7 is how much? 14% or 15% and 70% possibly would need 20. So, this is 15 to 20 years, this is 25 years and 25 to 30 years. So, what you might find when it is a large number of buildings, not 7 buildings are too small, when you have a large number of buildings or it is a large organization dealing with large number of buildings, there might be a possibility, there might be a probability that some 15% would require repair earlier, some 70% would possibly require as I have estimated, and another 15% will require later. Now, what will be its implication in the second cycle? The one which are repaired here now, right, this would, ones which are repaired here now, this would actually now 5 years, 10 years, 15 years, 20 years. So, heat it will get distributed here in this manner, 70% of 15%. So, this after after 20 years most of it again would require repair, but it may so happen that 15% of it requires repair earlier and 15% requires earlier. So, this will be actually 0.15% of 15%. So, that is 0.025 2 to 5, 0.02% will be here, 0.02% will be here and 105% will be 2 to 5. So, if you sum them up, this will get distributed in this manner, while this 70% will get distributed, 70% will get distributed in some manner like this. It's 15% of the 70% will come here and 70% of the 70% will come here, and there will be another small amount here, and third one also. So, you will find that in the next cycle it gets spreaded over a longer period of time, with the peak going to 49, maybe 49 plus 0.002 and 51% or something like that instead of 71. So, it gets spreaded over a period of time. So, there is an uncertainty, the probability is involved, and that again tends to even out in case of a large estate. But then this all presupposes that you will have an yearly inspection, 5-yearly plan and yearly inspection. In that case, you can find out that the cost of maintenance by and large would even out in a large estate over a period of time. It will even out, or they would tend to remain similar, same, does not have too much of fluctuation, with certain percentage variation you can do it. What all, why I am telling about all this? Because this allows us to do a planning of those maintenance work. Otherwise, it is very difficult and economize on the whole thing, make it more efficient. You can do planning, while if you do ad hoc basis, just a complaint comes and you observe some problem or some complaint comes and then act onto it, in that case it would be extremely costly, because doing it time to time on an emergency basis is always costlier than doing it in bulk, even though some things are fairly remain good. So, this is what is we call advantage of the maintenance profile, and it can even out, and you can plan right in the construction phase, make a maintenance manual when one should do what and that kind of thing. Now, another example. So, example of this repair cost being cheaper than replacement cost being cheaper than repair cost. I have given you roof covering, there may be similar many other situations, but few one I would like to bring into your attention. One of them is a lamp replacement. Now, this is done quite often in industrial buildings, or it can be done even in IT, for example, IT or similar hospital or similar sort of thing. Now, one thing, two issues are there. Even modern lamps CFL and LEDs, they too will have similar kind of thing, only thing their life is longer. The two things are important. One is the output from the lamp. That means the lumen output. The light is measured in lumen, light output is measured in lumen. That is basically, lumen is something synonymous to watt actually, but much smaller value. So, lumen output means actual light energy output. One is electrical consumption, other is a lumen output. So, for 1 watt lumen output would be how much, for example, earlier 40 watts would have something like 2250 lumen or something like that. Current ones might have, for 15 watt it might be giving or maybe 8 watt or something might be giving similar kind of lumen output. Now, this lumen output tends to reduce down with time, but at a slower rate. So, that is not an issue at all, that it's still lumen output will still be sufficient. So, you do not replace lamp on the basis of their lumen output, but what happens is, if you look at incandescent lamp, they will start failing, fusing out. Simply they will give up, the wire, the filament will break or something of that kind. Now, life of these lives are actually tested. These lives are generally tested. They do actually kind of an accelerated testing, that means subject them to similar kind of failure in higher voltage, because after all heat will come. So, one can do testing and find out the life. So, what they do is they find out what is called mortality curve. The mortality curve is which time how much percentage is failing. So, time versus percentage survivor, that is what is plotted. So, that is called a mortality curve. So, based on that mortality curve, one thing you will find that initially it does not fail much, but suddenly the rate of failure is very high. So, in that case you do not do patch repair, I mean one lamp has got bad, change it, no. You might even find it economical to change all the lamps, but now this time would be much higher, because it is now the life of CFL or LED lives are longer, lamps are longer. Earlier much shorter period you do have to do replacement, maybe you will have to do it more.